S. Muthukumar, Assistant Professor, Department of Mathematics. In this video, I am going to explain about the Markov process. Markov process comes under the module random process for ECE students. Markov process is a special class of random process. If the future behavior of any process is depends upon the present behavior, not on the past behavior, means it is known as Markov process. So it is defined mathematically in the name of Markov chain. If for all n, probability of xn equal to an given that xn minus 1 equal to an minus 1. That means xn means future behavior, xn minus 1 means present behavior, then xn minus 2 equal to an minus 2. It comes under past behavior equivalent to probability of xn equal to an given that xn minus 1 equal to an minus 1. That means the happening of the event n depends upon the event of happening of n minus 1, not on the past events. Here the terms a0, a1, etc. an are defined as states of Markov chain. Next one, the transition probability matrix. So it is a matrix defined for the Markov chain, where Pi is the one-step probability from state I to state J. That means conditional probability of state I to state J. A matrix is said to be stochastic if it should satisfy these two conditions. That means Pij greater than or equal to 0. That is, all the entries in that matrix are positive only. And also sum of Pij equal to 1. That means sum of each row is equivalent to 1. So if any matrix satisfies these two conditions, means that matrix is known as stochastic matrix. Okay. Next one is TPM of, if P is the TPM of regular Markov chain, then pi P equal to pi is the steady state vector. That means steady state vector means the sequence of happening of the events for all the states are following unique distribution. That means steady state probability vector. And also the second one condition is sum of all the probability values equal to 1. Now based on these definitions, we are going to discuss about one problem. So it comes under a long run problem. Now see this statement of the problem. A salesman territory consists of 3 cities A, B and C. He never sells in the same city on successive days. If he sells in city A, then the next day he sells in city B. However, if he sells in either B or C, the next day he is twice as likely to sell in city A as in the other city. In the long run, how often does he sell in each city? So the process of a salesman is given for 3 cities. We can formulate this statement into a matrix by using the concept of TPM, transition probability matrix. So the behavior of the salesman comes under the Markov chain. That means the sales in the city depends upon the present day only for the next day, not on the past days. Okay. Now formulate the matrix corresponding to this statement. The salesman territory consists of 3 cities. So the problem comes under 3 states. So here the states are denoted by A, B and C. He never sells in the same city on successive days. So using these conditions, we can fill the diagonal entries. Suppose if he sells in the first day in city A means the next day he definitely does not sell in the same city. So its corresponding entry becomes 0. Similarly for the B and C city also. Then come to the next statement. If he sells in city A, then the next day he sells in city B. Suppose the first day of the week he sells in city A. The next day he moves to the city B. He does not go to the city C. So its corresponding term is 0. Here we have to follow the rules for TPM. There are two rules. One is all the entries are greater than or equal to 0, and the another is sum of each row is equal to 1. Now see the first row. Here there is no way to sell 2 days in the same city. So here the entry is 0. Again, if he sells in city B, A means the next day he moves to the city B, not on C. So its corresponding entry is 0. So the remaining value, so follow that value condition. Sum of each row is equal to 1. So we have to fill 1 here. Okay, this is the for the city A. Then come to the next statement. However, if he sells in either B or C, so the first day he may sells in city B or C, then the next day he is twice as likely to sell in city A as in the other city. For example, the first day he sells in city B, so the next day he definitely sells in city A, but the quantity is twice in the previous day. Okay, so the statement is for the third row. If he sells in city B for the first day, the next day he moves to the city A, but the quantities for the 2 different days will be vary. The first day if he sells a quantity of X means the next day he sells a quantity of 2x in the city A. Okay, so now we have these two terms, x plus 2x equal to 1, because of sum of each row is equal to 1. So x plus 2x equal to 1 means 3x equal to 1, then x equal to 1 by 3. So the quantity of selling in city B is x, which is equal to 1 by 3. It's twice in A, so which is equal to 2 by 3. Similarly follow the city C also. If he sells in city C means the next day he will sells twice as his sells in city C. That means if the quantity of city C is 1 by 3 means the next day the quantity of sellings in city A is 2 by 3. Okay, so this is the TPM of given process. Now check whether it is satisfies the condition or not, TPM condition or not. So now add all the values in each row, which is equal to 1. So it satisfies the condition. And the for the second and third row also, that is 2 by 3 plus 1 by 3 equal to 1. So it is a TPM for the given process. Now apply the steady state distribution to this TPM matrix for calculating the probability of selling in each city. So this is the condition for steady state probability. It is steady state vector. There are 3 states. So use 3 values, pi 1, pi 2, pi 3. Pi 1 for city A, then 2 for B, 3 for C. Here the condition is pi into P equal to pi and the sum of vector equal to 1. So from this equation 1, this is the steady state vector, then this is P is the transition probability matrix equal to steady state vector. Now multiply the left side matrices and equate with the right side vector. So for the first term, take this total vector and multiply with the first column. So pi 1 into 0 0 pi 2 into 2 by 3 plus pi 3 into 2 by 3. So it is given here 2 by 3 plus pi 2 plus 2 by 3 plus pi 3 equal to pi 1. Similarly, multiply the second and third column also, and also use the conditions pi 1 plus pi 2 plus pi 3 equal to 1. Now calculate the values of pi 1, pi 2, pi 3 from these four equations. For that, here the pi 3 values are given in terms of pi 2. Similarly, find the value of pi 1 in terms of pi 2. For that, use any one of these two equations. I am using the second one. From this one, pi 1 equal to pi 2 minus 1 by 3 pi 3. So replace the pi 3 value here. So which gives pi 1 as 8 by 9 into pi 2. Now pi 1 is in terms of pi 2 and pi 3 also in terms of pi 2. So use these two equations in the sum of probability vector equal to 1. So pi 1 plus pi 2 plus etc. pi 3 equal to 1. So using this equation, we can get the value of pi 2. Pi 2 equal to 9 by 20. So in terms of probability, 45%. So the probability of selling by salesman in city B is 45%. So using this pi 2 value in these two equations, pi 1 equal to 8 by 9 pi 2 and pi 3 equal to 1 by 3 pi 2. So we can get the value for city C and A. The probability of selling in city C is 15%. That means 0.15. The percentage of selling in city A is 40. So this is the statement of the problem. If he follows this manner, means finally at the end of this month, the sales rate for each cities are 40, 45 and 15% for the cities A, B and C respectively. Okay. So next come to the next one problem. So in this case, we are going to find out the probability of takes the train on the third day. That means here the problem is a man either drives a car or catches a train to go to office each day. He never goes 2 days in a row by train. But if he drives one day, the next day he is just as likely to drive again as he is traveled to by train. Now suppose that on the first day of the week, the man tossed a fair dice and drove to work if and only if a 6 appeared. Find the probability that he takes on the train on the third day. On the second one, the probability that he drives to work in the long run. So this problem deals with the behavior of a man. Man follows the rule for going to the office. So there are two ways. One is train and another one is car. So he used to follow some rules to travel train or car. So based on this statement, we can formulate a TPM, that is transition probability matrix. So there are two states only because of car and train. So it is mentioned here, train and car. Now fill these two values, that is 2 by 2 matrix values. The first statement, he never goes 2 days in a train. That means if he goes on the first day by train, means next day he definitely does not go by train. So its corresponding entry 0. So the remaining only one entry. So this should be 1 because of sum of these two entries should be equal to 1. Then come to the second statement. If he drives one day, the next day he is just as likely to drive again as he is traveled by the train. If he drive one day, means the next day he may drive again or he may go by train. So there are equal possibilities for going to the office by train or car. So divide it here. 1. Divide the value of 1 for 2 possibilities. That is 1 by 2 plus 1 by 2. So this is the TPM for the given process. So that is Markov process. Now find the first question is find the probability that he takes a train on the third day. So subject to the condition, the first day of the week the man tossed a fair dice and drove to the work if and only a 6 appeared. So on the first day he throw a fair dice. If 6 appeared means he will go to the office by car. If not, if any other values appear means that means 1, 2, 3, 4, 5 appear means he choose the train to go to the office. So based on this condition, the initial state probability is defined here. That is p power 1 for the first day. So probability of choosing train, comma probability of choosing car. So probability of choosing car is the probability of getting 6 and throwing a fair die. So the possibility of getting 6 and throwing a fair die is 1 by 6. So probability of t is the probability of getting non 6, that is other values 1, 2, 3, 4, 5 and throwing a dice. T is equal to 5 by 6. So on the first day the probability of going to the office by train is 5 by 6 or drive to the car is 1 by 6. So next find the second day possibilities. So that is day 2 for day 2 p square. So it is defined by the formula, that is previous value. That is, now remember the concept of Markov chain. That is future value depends upon the present value, not on the first one. Okay, so that means for the second day we can use the value of first day, that is p power 1 into p value. So multiply these two matrices. So this is the probability of that man go to the office by train or car on the second day. For the train, probability value is 1 by 2. For the car, probability value is 11 by 12. Okay. For the next day, that means third day. So p power 3. So use the previous day. That means present day. This is future. This is present, p square present, p1 past. So use the present probability value here, so that we can get the value of probability of train or car. For train 11 by 24, for car 13 by 24. That means the probability of man travels by the train on the third day is 11 by 24. Thus this is the answer for the first solution. That is probability of he takes a train on the third day. If he getting 6 in a tossing of coin. Okay. Then the long run. So in this case assume the steady state distribution. There are two states. So pi equal to pi 1 comma pi 2 subject to the condition pi into p equal to pi and pi 1 plus pi 2 equal to 1. So from the first equation we can get the two equations, 0.5 into pi 2 equal to pi 1 and pi 1 plus 0.5 into pi 2 equal to pi 2, and use these two equations in equation 2 to get the value of pi 1 and pi 2. So pi 1 equivalent to 1 by 3 and pi 2 equal to 2 by 3. So pi 1 for train, pi 2 for car. So if you follow this manner means the probability of choosing train to to go to the office by a person is 1 by 3. For the probability of choosing car is 2 by 3. Okay. Thank you.